Okay, I'll share my screen now. Okay, so in the previous lecture, we were discussing the operation of a three-phase voltage source inverter in 180-degree conduction mode. And in the 180-degree conduction mode, the each switch conducts for 180 degree. Or half of the time period. So if the fundamental output is required at 50 hertz, each switch will operate for half of the period. Okay. So S1 will operate for half of the period, and S4 will operate for the rest half of the period. And there has to be a gap between the turning off of S1 and turning on of S4. And that's called the delay time or the dead time. That is practically always it is there in order to save the DC link. If you switch on S1 and S4 simultaneously, the DC link will be short circuited. Okay. Next, we wanted to show the waveform for the phase voltages and line voltages. So to get the phase voltage and line voltage, we have analyzed the circuit for each mode of operation. So we see that there are 6 modes of operations, and for each mode we have indicated which switch is on in that period. So in mode 1, we see that S1, S5, and S6. S1, S5, and S6 are on. Then mode 2, S1, S2, and S6 is on. How we know that S1, S5, and S6 is on? That we know from the switching signal that we are giving to them. So we see that in this period, this is high, switch S1 is high, switch S5 is high, and S6 is high. So that means 1, 5, and 6 are conducting, and the others are non-conducting. So in each mode, there are 3 switches that are on and 3 switches that will remain off. So in this way, we found all the 6 switches that are being on, and then we analyze assuming the resistive load, and we found the different phase voltages. And from the phase voltages, you can next find out the line voltage by subtracting VAB is equal to VAN minus VBN and so on. So we found these voltages, and I ask you to complete the task for mode 3, 4, 5, and 6. And then we plot the phase voltages. So the phase voltages that you will plot will be like this. So this is your VAN. This is VAN, 1/3 of VDC, then 2/3 of VDC, then 1/3 of VDC, then minus 1/3 of VDC, then minus 2/3 of VDC, then minus 1/3 of VDC, and then this is one cycle. Okay. So in each cycle, you see that it has 6 steps: 1, 2, 3, 4, 5, and 6. So 6 steps, but this is not called 6-level inverter. This is not 6-level inverter. Remember, not 6-level inverter. It is 6-step waveform. So this is phase voltage. Phase voltage. What is phase voltage? The voltage that appears across the load of the inverter. The voltage across load of the inverter, phase voltage, is of the waveform with 6 steps. Okay. This is still a 2-level inverter. Why it is called 2-level inverter? Because the pole voltage, we define it from the pole voltage, this voltage. So pole voltage will acquire 2 values, either VDC or 0. Okay. If it has a split DC link, then it will be having 2 level. One is called plus 0.5 VDC, another is minus 0.5 VDC. So in both the cases, it will have only 2 levels. The pole voltage will be 2 level. So it is called a 2-level inverter, but the output voltage waveform is having 6 steps. It is having 6 steps, and it is 6-step voltage And what are the steps? 1/3 VDC, 2/3 VDC, 1/3 VDC, minus 1/3 VDC, minus 2/3 VDC, and minus 1/3 VDC. Okay. So this is VAB, this is VBC, this is this is VAN, this is VBN, this is VCN. Okay. Now, what you do that to get the line voltage, what you do that you to get VAB, which will be VAN minus VBN. So when you subtract this, you get this as your line voltage. So line voltage is having a peak value of VDC and 0, and then VDC and then 0, like this. So it is 3 level what you get in the line voltage. So line voltage have 3 levels. What are the levels? Plus VDC, 0, and minus VDC. These are the levels. And what are the levels here? The level that you see, 1/3, 2/3. Okay. So you see here the peak is going only up to 0.666 VDC. The line is going up to VDC. So this is your line voltages. Now, please plot common mode voltage. Plot common mode voltage. How you will plot common mode voltage? Common mode voltage VNN is minus 1/3 of VAN plus VBN plus VCN. Now, what is VAN, VBN, and VCN? This you can consider as VAN. This you can consider as the pole voltage. Okay, this you can consider as the pole voltage VDC. So let me show you for one mode, and then you can find yourself. So in this mode, this is plus VDC. This is S5. What is S5? S5 is C. So this is also plus VDC, and S6 is high. So S6 is what? S6 is at VBN. This is at the in the phase B. So phase B is 0. We call it phase B as 0. So what will be the VNN? VNN will be minus of 1/3 VDC plus VDC. So this gives you minus 2/3 of VDC. So minus 2/3 VDC. Next, you look at the mode 2. So mode 2, VAN is again VDC. VAN is VDC. Just let me take the call anyway. Yeah, I'll talk to them later. No problem. So this is VDC, and this VBN is again VDC, and this is 6. Where is 6? Yeah. So no, this is this is S2. S2 is here. S2 is here. So this is 0 and S6 0. So these two are zeros. So we have VDC and then 0 and 0. So that means the VNN will be minus of VDC by 3. So this is what you see for the common mode voltage. So please complete for all the 6. Okay. Now RMS current for the resistive load. So the voltage is this. This is the voltage of or output voltage of this is the phase voltage. Okay, the half cycle only. So for the half cycle, because it is symmetrical, just you need half cycle to get the RMS value. So what is the current here? The current here will be, this is 1/3 of VDC. This is 2/3 of VDC. So what is the current here? Current here is 1/3 of VDC divided by load resistance. And what is the current here? 2/3 of VDC divided by load resistance. And what is the current here? 1/3 of VDC divided by load resistance. So you know the current. and this the period also you know from 0 to pi by 3. So it is given as 1 by pi, which is 1 by t. Then current square into the time period, which is pi by 3. Then current square into time period, current square into time period, and then you calculate this, you get this as your RMS value. So IRMS 0.471 VDC upon RL. This is the RMS value of the current for a 6-step waveform, 180-degree conduction mode. Do you understand? Do you have any question here?
Question.
So this is a straightforward question. It says that a 3-phase inverter is connected between a balanced star-connected resistive load of 10 ohm and 250-volt DC supply. The inverter frequency is 33 hertz, and the switches conduct for 180-degree conduction mode. Calculate the RMS current and the load power. So RMS current is 0.471 VDC by RL. The power is 3 into I square into RL. So just direct substitution, you get this. Now let us see the harmonic spectrum, how the harmonic component looks like in a 3-phase 180-degree conduction mode, square wave or a 60-step operation of inverter. So the Fourier series of the output voltage has a fundamental frequency equal to the switching frequency, and so switching frequency and fundamental frequency are same in the case of the 180-degree conduction mode, and harmonic frequencies are of the order of 6k plus minus 1. So 6k plus minus 1. Now if you put k is equal to 1, if you put k is equal to 1, it will be 5th harmonic and 7th harmonic. When you put k is equal to 2, it will be 11th harmonics and 13th harmonics, and so on. So these will be the harmonics in the output voltage waveform. So you see in the PWM, the frequency component, the harmonic component appeared at switching frequency. Here they are appearing at low order harmonics are appearing here, 5th harmonic, 7th harmonics, 11th harmonics, 13th. But there will be no multiple of 3. 3n harmonics is not there because it is 3-phase system. In 3-phase system, you will not have 3n because they cancels out each other, and even in the line to line. So there will be no multiple of harmonics for 3. That means 3, 9, 15 will not be there. Okay. So third and multiple of third harmonic do not appear in the 3-phase inverter. And even harmonics are also absent. There is no second, fourth, sixth, because there is no asymmetry in the waveform. The waveform is completely symmetrical along the x-axis. So that's why the up area and the down area are the same. So you do not see any even harmonics. Okay. And the line to line voltage is given by this relation 4 VDC by n pi into cos of n pi by 6. And the phase voltage, this is line voltage, line to line, nth harmonics. Now if you put n is equal to 1, it will give you the fundamental. And line to neutral is given as 2 VDC by 3 into n pi, and with this. Okay, this is nth harmonic. If you put n is equal to 1, it will give you fundamental. So what will be the fundamental? Line to neutral, 2 VDC by 3 pi into 2. So that means it will be, okay, so this is, here it will be 2 plus pi by 3. Pi by 3 is what? Cos pi by 3 is half, and minus 2 pi by 3. So how much will be this? 2 pi by 3, 120 degrees. So this will be 120 degrees is what? Cos 120 degrees is minus 1. 120 degree cos is minus half. This is half, this is minus half. So it is 3. So this becomes 3 and 3 cancels out. So what you have is VDC upon pi. 2 plus half plus half. So 2 plus 1, 3. So this is the line to neutral. Okay. And this is line to line. So this is the peak value. This is the peak value. Peak value. So what is the RMS value? So line to line RMS is given by root 2 by 3 VDC. UVDC. And fundamental RMS line RMS value is 0.7797 VDC. And fundamental RMS phase voltage is given by 0.45 VDC, fundamental RMS. The output frequency can be controlled by changing the switching frequency. The magnitude of the output voltage depends upon the value of the DC voltage. To control the output voltage of the 6-step inverter, DC input must be adjusted. So you see here, because it depends upon VDC. It depends upon VDC. So how you change the VDC? VDC you can change from the source side. From the source side. Here you can change VDC, then here you will get different voltage. Now this is an example on 6-step 3-phase inverter. For the 6-step 3-phase inverter, the DC input is 100 volt. So DC linked voltage is given as 100 volt. And the fundamental output frequency is given as 60 Hertz. Load is star connected with each phase of the load as a series RL. So R is equal to 10 and L is equal to 20 millihenry. Determine the total harmonic distortion of the load current. So total harmonic distortion in the load current is given by this relation. IN square RMS upon I1 RMS. So we have to find out the fundamental current and the harmonic currents. So to get the current is Vn over Zn. Current is Vn over Zn, but this is peak value. Remember, we have to get the RMS. So now, what is Vn line to neutral? You know what is Vn line to neutral? This is this. So VL and neutral, phase to line to neutral, phase to VNLN. VNLN means it is line to neutral. So this line to neutral formula is given. You can put the value of N and you can get the value of voltage, and that voltage you put here and you get the current. Okay. So for the fundamental, the line to neutral voltage is how much? Let us calculate. 2 VDC upon pi. So VDC is 100. So this become 200 divided by pi. So this gives you, this is your V1 line to neutral. So this is fundamental. This gives you 63.6. And the impedance is under root R square plus omega naught L square. So you get as 12.5. Correspondingly, you calculate the current. So this is the current, and then you calculate the RMS. So you calculate the RMS 5.08 divided by 2 root So this current, this is obtained as IN divided by √2. So we calculate for 5th, 7th, 11th, 13th. So few harmonics we have calculated, and then you use this formula to obtain the total harmonic distortion. Okay. Any question here?
All clear.
All clear? Okay. Next, we discuss the PWM of three-phase inverter. So what we do that each switch is controlled by comparing a sinusoidal reference or the modulating wave with a triangular carrier. The fundamental frequency of the output is the same as that of the reference or modulating wave frequency. The amplitude of the output is determined by the relative amplitude of the reference and the carrier wave, that is the modulation index. So by controlling the magnitude of the triangle, over the sine wave, you can control the output amplitude. So output amplitude is controlled by modulation index, and the frequency is controlled by the frequency of the reference wave. And you compare the triangle with sine wave. Okay. Now, you have 3 legs. You have 3 legs. So to generate the switching pulses for the first leg, sine wave A and triangle is required. To obtain the switching signal for phase B, we need phase B sine wave and the triangle. Okay, and for phase C, we need 120 degree phase shifted sine wave compared with the triangle. Okay, so this is the triangle. One common triangle is there, and you compare with 3-phase sine wave. Now this is phase A. So the switching signal that will be obtained by comparing this sine wave with the triangle, that will be given to leg 1. Okay, and the switching signal that is generated from comparing this triangle, this sine wave with the triangle, will be used for switching the leg B. And then similarly, this is for leg C. So when you compare this, you get the switching signal, you turn on and off the switches accordingly, and we get this as the line voltage, this as your phase voltage. Okay. Any question? Now the harmonic performance. So you see, in the case of 6-step waveform, we have the fundamental, then we have 5th harmonic, then we have 7th harmonics, then we have 11th harmonics, then we have 13th harmonics, and so on. For PWM, we get the fundamental at fundamental frequency, fundamental component. Then we get the component at the band, side band of the switching frequency. So at the switching frequency, we do not have anything. How much will be the switching frequency? Switching frequency is controlled. You see, the switching frequency is about, like 2 kilohertz to 20 kilohertz, like this. So we get this as the switching harmonic spectrum. And this is the table for 3-phase PWM, line to line voltage. This is line to line voltage. So fundamental, this is for the MF is equal to 2. This is for MF is MF is equal to, what is MF? MF is frequency of triangle over the frequency of the sine wave. Okay, so this is all about the two-level inverter. Next, we have multi-level inverter. How we get the multi-level inverter? You see, the H-bridge inverter produces output of VDC 0 and minus VDC. If you have two leg and you connect a load here, you connect positive DC bus here and negative DC bus here, then the voltage across the load, voltage across load will have three values, either plus VDC or minus VDC or 0. When we will have plus VDC, the plus VDC, when this is on and this is on, we get plus VDC. And when this is on and this is on, we get minus VDC. And when both of these are on together, the either top two switches or bottom two switches, then we get 0. So we get 3-level voltage here. We get 3-level voltage here. So the basic H-bridge switching concept can be expanded to other circuit that can produce additional output voltage levels. So these multi-level output voltages are more sine-like quality and thus reduces harmonic components. The multi-level inverter is suitable for applications including adjustable speed motor drive and interfacing renewable energy sources such as photovoltaic to the power grid. So what we see that the output voltage in the case of multi-level inverter will be like this. So more number of levels, as the number of level increases, they are become close and close, and they are like, they are more and more like sine wave. They are looks more close to sine wave. So if they look more close to sine wave, the overall harmonic performance is better. The harmonic are low, the THD will be low. Total harmonic distortion will be low. In case of a two-level inverter, if we want to get very good waveform, we have to increase the switching frequency. Switching frequency has to be high. Then we get good waveform. But good waveform we get on the expense of high switching frequency, high switching losses, because you increase the switching frequency, so the device on and off many times. So that causes loss and hence poor efficiency. So you get one better thing, that is you get better quality output, but the switching losses will increase. Now here you can get the similar output power quality at lower switching frequency. Okay, because you have many steps in the output, so it resembles more like a sine wave. Okay. Moreover, here you see the dV by dt, rate of change of voltage, is high. Why? Because we have only two levels of the output. If we talk about the pole voltage, it's only two level, VDC and 0. Okay, so dV by dt will be what? VDC by the time at which you are switching on and off. So this will be dV by dt. So high dV by dt means the stress on the switches is high. So what we want to do, if we reduce this to 0.5 VDC, then the stress or the dV by dt is reduced considerably. If we reduce it further, 0.1 VDC, this further reduces. So in the multi-level inverter, the dV by dt is low because the step size is small. You see, the step size are small. It will jump from 100 volt to 200 to 300 to 400 like this. But if you have two level inverter, it will go directly from 0 to 400 and then from 400 to 0. So like high voltage on and off. So that is like high stress on the device. But if it is like 100 volt, then you make 200 volt, then you make 300 volt, then you make 400 volt in time interval, then you have less stress on the switch. So the dV by dt is low in case of multi-level inverter. Total harmonic distortion is improved in the case of multi-level inverter. Okay. So we try to use multi-level inverter. Now there are many types of multi-level inverter that we can work on. So there are three like fundamental type of multi-level inverter that we will discuss here, and there are like thousands of variations on that, but we don't look into those. There are three different types of multi-level inverter. One is called cascaded edge bridge. Another is called neutral point clamped, NPC, neutral point clamped, or diode clamped. So it is called diode clamped or neutral point clamped. And another is called flying capacitor inverter, flying capacitor. So these are the three names: cascaded edge bridge, NPC inverter, neutral point clamped inverter, and flying capacitor inverter. Now what is cascaded inverter? You have one edge bridge, you take another edge bridge, you connect them in cascade. You can have two separate DC link, or you can, this is like VDC1, this is VDC2. But VDC1 should be equal to VDC2, otherwise the output level will be of different heights, different heights. So in this, if you cascade, you see what we did, I cascaded to H bridge. Now my output here will be 5 level. Output will be 5 level. If I cascade 3 of them, one more, it will be 7 level. If I cascade one more, it will be 9 level, like this. But what you need here, you need isolated DC sources. This and this are different sources. They are not the same. Although they have equal magnitude, but they have a different isolated DC source. So this is, you can consider this as a PV arrays, a set of PV arrays. This is another set of PV arrays, photovoltaic arrays. So this is called multi-level inverter. So one multi-level inverter method uses independent DC sources, each with H bridge. So independent DC sources, this DC independent, and they are cascaded. A circuit with two DC sources is shown in the next slide. The output of each H bridge is VDC minus VDC or 0. So we know that the output of this is VDC 0 minus VDC. Similarly, the output of this is VDC 0 minus VDC. But when you combine them, you get 5 levels. What are the different 5 levels? 2 VDC, VDC 0 minus VDC minus 2 VDC. These are the 5 different levels that you will get. So this is the output of inverter 1. This is the output of inverter 1. And if we V1, now if we place another waveform over this, this is the output V2. This is output V2. This V2. So we switch it at different angle. This was switched at alpha 1 angle. This is switched at alpha 2 angle. Now by doing this, you can see that we get 5 levels. So what are the 5 levels? This is 0 level. This is VDC level. This is 2 VDC level. This is VDC level. this is 0, this is minus VDC, and this is minus 2 VDC. So we count like this. You start from the top, from here, 2 VDC, VDC, 0, minus VDC, minus 2 VDC. So we get 5 different levels. Any question here?
Yes, doctor.
Yes.
Does that mean if they have the different width, does it mean that the switching frequency for both of them will be different?
The switching frequency for the two should be the same. You switch them at the same frequency. You switch them at same frequency. But switching instant is different here. You see, switching frequency means what? Switching frequency is 1 by T. The time period is the same. You see, the time period is the same, but it is on at different alpha. This is on at different alpha. So this, the module 1, this is called module 1. This is called module 2. Module 1 you switch at alpha 1, and module 2 you switch at alpha 2, different instead of time. So that you superimpose their waveform, so that you superimpose their waveform. Now, what should be the value of alpha 1 and alpha 2? What should be the value of alpha 1 and alpha 2? That we will obtain. That we will obtain. How much will be alpha 1 and alpha 2? We have to solve the equation to get the value of alpha 1 and alpha 2. Okay, we need numerical solution to get what should be the value of alpha 1 and alpha 2. So, the Fourier of this step waveform, the Fourier of this step waveform is this. 4 VDC by pi cos n alpha 1 plus cos n alpha 2 sin n omega naught t over n. So the Fourier coefficient is this. Fourier coefficient is this. Now the modulation index is defined in this. This is equation number 1, say MLI equation 1, that is multi-level inverter equation number 1. The modulation index is the ratio of the amplitude of the fundamental frequency component V0 to the amplitude of the fundamental frequency component of the square wave of the amplitude 2 VDC. So what was the amplitude in the square wave operation? That was this. So you divide V1 with respect to the what was in the originally in the square wave. So when you divide this, what you define is the modulation index. So the modulation index will be cos alpha 1 plus cos alpha 2 divided by 2. This is how you define modulation index in multi-level inverter when you have two cascaded edge bridge. Now, some of the harmonics can be eliminated from the output voltage waveform with the proper selection of alpha 1 and alpha 2. For the two source converter, that is two module, harmonic n can be eliminated by using delay angle such that cos m alpha 1 plus cos m alpha 2 should be equal to 0. Another equation is that cos alpha 1 plus cos alpha 2 is equal to 2mi. This is defined from here, modulation index. So this is one equation, cos alpha 1 plus cos alpha 2 is equal to 2 times modulation index. And another equation that comes from the, because if you want to make nth harmonic 0, so if you want to make nth harmonic 0, so this term should be 0. So cos of n alpha 1 plus cos of n alpha 2 should be equal to 0. So you get this as equation number 2. So now you solve these two equations, you can get what is the alpha 1 and alpha 2 value, so that we can eliminate certain harmonics. Suppose if you want to eliminate fifth harmonic, so it will be cos 5 alpha 1 plus cos 5 alpha 2 is equal to 0. Another equation, cos alpha 1 plus cos alpha 2 is equal to 0. Now we have to solve these two equations using analytical numerical approach. And there are many methods that have been proposed in the literature to solve these equations. They are called selective harmonic elimination. This is called selective harmonic elimination, because you select which number of harmonics is to be eliminated. If you want to eliminate fifth harmonic or seventh harmonic or ninth harmonics, then accordingly you choose the value of alpha 1 and alpha 2. Okay. Any question? Now, example on this. For the two source multi-level inverter, when it says two source, that means two module cascading 5-level inverter with VDC is equal to 100 volt. Determine the Fourier coefficient 2 is equal to 40 degree. Determine alpha 1 and alpha 2 such that the third harmonic is eliminated and modulation index is 0.8. So Vn is 4 VDC over n pi cos n alpha plus cos n alpha 2. So 4 into VDC over n into pi cos n 20 degree cos n 40 degree. This result in V1 is equal to 217, V3 is equal to 0, V5 is equal to this, V7 is equal to this, V9 is equal to 0. Note that the third, ninth are eliminated. The even harmonics are not present. Even is not present because you have symmetry around this 0 axis. If they are the same, even is not there any. Now, modulation index is calculated by using this formula. So the amplitude of the fundamental frequency voltage is therefore 85.3% of the square wave of plus minus 200 volt. So the DC link voltage is 100 volt. Correspondingly, we found what are the different harmonic component. That was part A. Part B, to achieve the simultaneous elimination of third and modulation index of 0.8, we require the solution of these two equations. Cos 3 alpha 1 plus cos 3 alpha 2 is equal to 0. Cos alpha 1 plus cos alpha 2 is 2mi. So this is equal to 1.6. I write here wrong. This is 2m1. 2mi modulation index. When you solve this using iteration approach, we get this 7.6 and 52.4. Now let us see the general case of cascaded edge bridge. So what is the general case? You see here, for example, if you have like module 1, module 2, module 3, module 4, module 5. Okay. So what will be the number of levels that we will obtain here? And these are the different voltages. So you see here, this is V1 at alpha 1. We switch at alpha 1. This is for V2. This is V3. This is V4. This is V5. And now when you superimpose them, you get this as your output. So what you get? 0. So I to count the level, I will count from here. Okay, from here to here. So level number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 levels. 11 levels. 5 VDC, 4 VDC, 3 VDC, 2 VDC, VDC, and 0. And then negative of that. So for k separate sources connected in cascade, there are 2k plus 1 possible level. This is general formula. If you have k number of modules, you will have 2k plus 1 level. So you see, if you have 2 modules, you will have 5 level for 2 modules. For 3 modules, 7 levels. For 4 modules, 9 levels. For 5 modules, 11 level, and so on. As more DC sources and edge bridge are added, the total output voltage has more steps, producing a staircase waveform that more closely approaches a sinusoid. You see, this very closely looks like sine wave. So the harmonic distortion is very less, harmonic content is very less, and very nice waveform you get. Power quality is very good. For a 5 source system, 11 levels are possible. And the Fourier coefficient of the staircase waveform for k separate DC sources, each of VDC magnitude, this is the formula for n, for k number of sources. So modulation index is once again defined by this. So it is modulation index is defined by this relation. Now here you see, if you have 5 source, determine the delay angle required for the 5 source cascaded multi-level converter that will eliminate this. So this is selective harmonic elimination problem. Selective harmonic elimination. Now you see here we have to eliminate 5, 7, 11 and 13. So 5, 7, 11 and 13 should be 0. And this is the standard equation for modulation index. 1 cos alpha 3, 4, 5 should be equal to 5 times mi. And mi is given as 0.8. So you get these 5 equations. Now there are many methods to solve these 5 equations. So we use those methods to find the different alphas, and these are the different alpha that we get. Okay. Any question here?
Doctor?
Yes.
In general, how many harmonics in max can we cancel?
You see, if you have like, it depends upon how many modules you have. If you have 2 modules only, you can eliminate only 1 harmonic. Okay. Any 1 harmonic. The lowest harmonic is 3rd. So you want to eliminate 3rd harmonic. But remember, if it is 3-phase system, there will be no 3rd harmonics. Okay. The minimum harmonic will be 5th harmonic. Understand? Now, if it is 3 modules, we can eliminate 2 harmonics at a time. 4 modules, we can eliminate 3 harmonics at a time, 1 less than number of modules. 5 modules cascaded, we can eliminate 4 harmonics simultaneously. This is the problem shown here. 5th, 7th, 11th, 13th. This we have eliminated. So whatever is the number of modules you connect in cascade, 1 you subtract. That many number of harmonics you can eliminate. Does this answer your question?
Yes, clear.
Okay. Oh, I will stop here. Then we'll discuss this other types of multi-level inverter, and that will finish the chapter. Okay. Any question you have or any discussion you want?
Is this the final chapter?
This is actually the final chapter, but I may give you like, one introduction to AC-AC converter. Okay. Just introduction, like no detail. In like half an hour like this. Okay.